Now finally get to the discussion of parameter learning without fully observed data in HMMs. And this is the most usual case in which HMM training is being done. So you do not know the latent variables. You do not know in the previous examples that we've been seeing that whether the coin being tossed was a fair coin or a biased coin. You don't know that sequence of states in a dataset. So in such cases, computing the MLE map could be hard. So in the previous derivation that we had done, if you notice, ZT was available. So thus it was not that difficult to compute the MLE and map estimates. But what is unavailable here is the values of ZT. So we could use some gradient-based methods for computing the MLE map, which would of course come with with their own set of problems such as local optima, etc. But it's often non-trivial to enforce constraints. These constraints come in the form like uh, the summation of pi j over j is 1. That is, you could start in one of the capital K states, right? And the summation of probability over starting in each of these j states has to sum up to 1, right? So often what we end up using is an algorithm known as expectation maximization. It's the same EM algorithm that you would have studied in some other concepts in data science and machine learning involving such as mixture of Gaussians, for example. So it's an iterative algorithm and it gives us some closed form updates, right? So we'll take a short detour from the HMM discussion and talk very briefly about the EM algorithm. So I'll be talking about the EM algorithm, and in this slide, please do not confuse the notation with HMMs, right? This is a more general discussion of the EM algorithm where we say that xi's are the observed variables, x1 through xn, for example, and zi is the latent or the hidden variable. So goal is to maximize the log likelihood, right? So the likelihood of observing the xi's given the model parameters theta. But if you notice that there is no mention of a zi term here, right? So that's because you have to marginalize that variable zi here in order to obtain this log likelihood, right? So think of it as you have to consider all possible values of state sequences or states in through which you could have obtained this value of xi. So we can alternatively thus write this expression as logarithmic summation over n different uh, values and the logarithmic over summation of over all zi values of the probability of joint probability of xi comma zi given theta. Right, so we've introduced the term zi and you have summed it up. This is the marginalization procedure. This is hard to solve because the logarithmic cannot be pushed inside these summations. Right. So given that this is hard to solve, we look at something else which we think is easier to solve. We define something known as a complete data log likelihood. Right? This is given by L subscript C of theta, which is given by summation over I equal to 1 to n, and the logarithmic of the probability of the joint of xi comma zi given theta. But we only just said a little while ago that we do not know what is zi, right? So thus LC of theta cannot be computed since zi is unknown. So we, instead of defining the complete data log likelihood, we define an expected complete data log likelihood, right? We end up defining a function q which takes in two parameters, theta and theta r minus 1. And this is an expectation over the complete data log likelihood given the parameters theta, given the data, and the parameter sequence theta in the previous iteration, right? So we define r to be the current iteration, and q is defined as an auxiliary function. If you don't get much of this, don't worry. We'll be looking at the specifics of this EM algorithm for the HMM algorithm. So as you would expect, expectation maximization, there is an expectation step and there is a maximization step. In the expectation step, we maximize Q. So you have an expected complete data log likelihood. You compute Q, which is you do the expectation given some set of parameters theta in a given iteration. And through this process, you end up computing something known as expected sufficient statistics. We are not going to delve into that details of ESS for now, but just let's look at an E step. You compute this function Q, and in the M step, you optimize Q with respect to theta. Right? So thus you obtain a theta R, where R is the current iteration, as the argmax over all the thetas, which is going to maximize this function. Right. So now let's forget about the specific details of EM, as I've mentioned. The generic details of EM, as I mentioned now. Let's talk about EM from the perspective of HMMs. Right. I'm going to not discuss all of the detailed derivations here. You could do that in your own time. So in expectation maximization algorithm, as we've discussed, it's an iterative algorithm, which means that you will have to repeat some processes or some steps till convergence. Right? This is a fairly standard iterative algorithm in that sense. In the E step, you're trying to infer the missing values, Zi, comma t. So I is here indicating the ith sequence, and t is the tth timestamp with that sequence, right? So if you remember, we said that this problem is hard, learning the parameters without the observed ZITs, because ZITs is unobserved, right? If ZIT is observed, then it's a fairly simple problem to solve. So what we're saying is that in the expectation step, we are trying to infer the missing values. So we're inferring Zi, comma t, given our current model parameters, right? So you have some model parameters that you start off with. Let's assume that you have started off with them randomly, right? You started off with a random theta, which is random pi a and phi. Based on that, you're trying to infer what ZIT could have been, right? And the second step is the maximization step. Now, this is similar to the discussion which we had just a few minutes back, where we say that we have already, so which is the same as the case as when you're trying to learn the parameters of an HMM, once you're given the hidden state sequences also, right? So since we have inferred the missing values ZIT in the previous step, we use those inferred values, and then we can just use MLE to obtain the optimal set of parameters theta, right? We can just maximize the log likelihood, assuming that we had already observed, we already had observed data, right? Which we truly didn't, but we inferred that in the E step, right? So I can now very briefly discuss about what is the sufficient statistics, ESS. These are the terms from the auxiliary function, which was Q, on which the MLE depends on, right? So there is a big definition or big formula for the Q function. We do not need everything in that. We just need to compute certain statistics from that function, which are known as sufficient statistics, ESS. So we'll be computing a term epsilon t I comma j, which tells us the probability of being in state I. So probability of being in state I at the tth timestamp, and being in state j at t plus 1th timestamp, given the observations and the model, right? So this is going to be one of the sufficient statistic term that we need to compute. So could you think about how you'd go about learning epsilon t ij, or could you think of writing epsilon t ij in terms of some of the quantities that we have already written thus far, like alpha, beta, etc. Think for a minute and try to come up with a solution for this problem. Okay, assuming you thought for a minute, so I'm going to draw this illustration to help you come up with a solution. I've drawn time step t minus 1, t and t plus 1. We say that at time t equal to, at time t, we are in the ith state, and at time t plus 1, we're in the jth state, and we're trying to compute this quantity, right? So the first hint I'm going to give you is, can you break down this quantity as, write this in the terms of a joint distribution, and then so if you have to write it in terms of the joint distribution, you just need to apply the Bayes rule here, right? So I'm going to write this term as the joint distribution. So basically just remove the conditional and bring this observation in the denominator here, right? So fair enough, just an application of Bayes rule. And now what I'm going to request you is to think about breaking down the numerator into terms that you already know, right? You know certain things like alpha and beta, right? So pause the video for a minute and think about how you'll be breaking down the sequence. So essentially, another hint is that you want to firstly model that you observe uh, the observations x1 through x small t, and you end up in state I. And you also want to see that what is the transition of going from state I to state j, and then observing x of small t plus 1. And then the other aspect of this chain is you start off with xt plus 1 equal to j, and you see the remaining part of the observations, which is similar to beta. So what I just said, I'm going to write that down. I've just broken this chain or this joint probability into individual terms, right? So I break this down into the probability of ending up in state I, and the observation sequence 1 through small t, right? Then we make a transition from state zt equal to I to zt plus 1 equal to j, which is given by aij. Then we look at the probability of emission of the observation x at time t plus 1, given that at time t plus 1 the hidden state was j, times the probability of the observation sequence from small t plus 1 through capital T, given that at time zt plus 1 you are in the jth state, right? And the denominator is just the normalization constant in this case. So can you pause and think for a minute that which of the quantities do you already know here? Okay, assuming you paused and worked out the quantities, we can write this first term, probability of zt equal to I, and the joint with the observations x1 through t shown in gray as alpha t of I, right? And then we have an aij term. We have another term which is probability of the observation being emitted as xt plus 1, given that the state is xzt plus 1 equal to j. So that's just phi j, and the observation x of t plus 1 times the probability of the observation sequence from t plus 1 through t, given that you're starting in state j at time t plus 1. So that's just beta of t plus 1 over j, or of j, right? And the denominator, as I said, is just a normalization constant. So you just take the numerator and apply the summation over all I and all j to be able to get the denominator, right? Okay, so we have defined epsilon t of I comma j. I'm going to be now rewriting gamma t of I. If you remember, we already used gamma t of I in one of our earlier lectures. Now we can rederive gamma t of I just using the epsilon t ij parameters, and that's what exactly we're going to do. So I'm going to again redefine or just revise the definition of gamma t of I. It's the probability of being in state I at the time t given the observations x1 through capital T and the model, right? So can you write the relationship between gamma t of I and epsilon t of I comma j? So the relationship between gamma t of I and epsilon t of I comma j is fairly simple. Epsilon t of I comma j is probability of being in state I at tth time step and being at state j and the t plus 1 at time step given the observations of the model. And for gamma t, we said that was the probability of being in state I. So, and given the observations and the model. So the only thing you need to do is to sum over all possible j states in which you can be at times at time t plus 1. Right? So that's effectively the formula for gamma t of I, summation over j running from 1 to capital K states of epsilon t I comma j. So we'll be now looking at the different summations over gamma t and epsilon t to better understand some of the terms which we require for the EM algorithm. The first question for you at this point is that what does summation of gamma t over I, where the summation is done over t, what does that really mean? Right. So gamma t of I was probability of being in state I at time t. If you sum it over all the possible timestamps t, then it is the expected number of times you are in state I, right, in a given sequence, right? The expected number of times you are in state I, or if you do the summation from t equal to 1 to capital T minus 1, this is giving you the expected number of transitions from state I. There's only a subtle difference between these two definitions. And if you just ignore small t equal to capital T, then both of these definitions are fairly similar. Okay, the next question for you at this point of time, and you should again pause the video and try to answer this yourself. What does summation epsilon t I comma j or over t equal to 1 through capital T minus 1 mean? Right. You should again look at the definition of epsilon t ij. That's the probability of being in state I and j in t and t plus 1 given the observations and the model. Right. So this is just telling us the expected number of transitions you're making from state I to j. Right. You have looked at the probability of the transitions across the different timestamps. So this is just the expectation of the transitions from state I to state j. Right. So let's now try to see what the HMM learning algorithm would be doing. Right. Let's take an example. So in this example, I have highlighted this is the same example which we have done before. In the previous case, when we did this example, we assumed that the states were known. But in this case, I've highlighted them in purple or violet, and I've mentioned that these are unknown, right? So we cannot make use of these. As I mentioned before in the EM algorithm, you will have to make some assumption or initialize the model parameters and then iteratively update them using the EM algorithm, right? So let's assume that I had done some random initialization and I came up with these parameter values, right? So now what I want you to do is, can you calculate if we go back to the algorithm? So what I said was, in the E step, you're trying to infer the missing values, ZIT, given the model parameters and the observations, right? So you already know the model parameters for this iteration and you know the observation sequence. Could you create or could you infer the missing values of ZIT for each ith sequence and the tth timestamp in the sequence? So that's the task that we want to carry out next. And for that, we need to compute the sufficient statistics, epsilon t of ij and gamma t of I. So we want to first compute the epsilon parameters for the first. By the way, we are only considering the sequence 1 for now. Right? So we want to compute the parameters epsilon 1 b comma b and epsilon 1 b comma f. So timestamp t equal to 1, and the different states are only bias and fair. So we have 4 such combinations. Right? So we can just write down the formula for epsilon 1 bb. That's the first thing which we're trying to compute. And we're just writing in this in terms of the definition that we had seen earlier. Epsilon 1 b to b is alpha 1 b times making a transition from b to b. And then once you made a transition, then you're observing at time t plus 1. And that observation is t times the probability of the observation sequence from t plus 1 through capital T, given that you're starting in state B, right? And this divided by the normalization constant. Now we've already seen how to calculate the alphas and the betas, right? So alpha 1 of B will just be pi b times phi b of x1 equal to h, and that would be 0.72. If you remember, alpha, the definition of alpha is the joint probability of seeing the observation sequence till time small t and being in that state I at the tth timestamp. Right. So since this is t equal to 1, the joint probability of the observation sequence and being in state bias is just being in state bias at time t equal to 1, and the observation x1 equal to h, given that you're in state bias. That's 0.9 into 0.8, which is 0.72. Now you want to calculate beta 2 of b, and if you remember, to calculate betas, you start off with calculating beta. You start off with initializing beta capital T equal to 1, and then you move backwards. So alpha is moving forwards, and beta is calculated using the backwards algorithm. So you initialize beta 4b equal to 1 and beta 4f equal to 1, and then you compute beta 3b. I am going to just skip the calculation in this recording and assume you can go through the video and you can go through the previous recordings to do the calculations yourself. It's an important exercise. I would highly encourage you go ahead and do these calculations. So finally, I calculated that beta 2b comes out to be 0.4192. So I can just write epsilon 1 b to b as the product of these quantities divided by the normalization constant, which I'm calling C, right? Similarly, for this given sequence S1, we can also calculate epsilon 1 f comma f, epsilon 1 f comma b, and epsilon 1 b comma f. So you can calculate the remaining 3 entries also, and you can very easily also do the normalization. Right? You can just sum over the relevant entries, and you don't explicitly need to compute the normalization constant then. So given that you know what is epsilon 1 bf and epsilon 1 bb, could you calculate gamma 1 b? Yeah, so that's just the sum of epsilon 1 bf and epsilon 1 b comma b. And similarly, you can compute gamma 1 f, which can also be computed just as 1 minus gamma 1 of b. Right? So we have thus far done some computations, and what we're saying is that if you consider only timestamp t equal to 1 and this given sequence S1, which is head tail HH, then the probability of Z1 equal to B is gamma 1B, and the probability of Z1 equal to F is gamma 1F, right? So we're not very certain, we're not fully certain whether Z1 is B or F, but we know a probability distribution over that. So in the case when we had all the observations, or when we knew the hidden state observations, we knew Z1 through Z capital T, we knew for sure what is Z1, Z2, and so forth. But now we do not know for sure, but we have a probability distribution, right? which is given by gamma 1b and gamma 1f. So the key insight here is that we'll be considering gamma 1j as the expected number of times that z1 equal to j, right? So this is coming back to the main concept. What we're trying to do is, let me take you back a few slides. The goal of the E step was to infer the missing values or infer the expectation over the missing values, right? So that's exactly what we have done thus far. We have now computed on expectations. In terms of expectation, how much, what is the expectation of starting in state 1 as a bias state versus the fair state, right? So you could do this for sequence 1, you could do this for sequence 2, and you could do this for sequence 3, right? So let's just assume some simple numbers. Let's assume for sequence 1 you get gamma 1b and gamma 1f as 0.5 and 0.5. For the sequence 2 you get gamma 1b and gamma 1f as 1 and 0. And for sequence 3 you get gamma 1b and gamma 1f as 0.8 and 0.2, right? So it seems much more likely that state 1 would be in fact the bias state, right? Given these three samples. But what we're now trying to do is let me walk you back again. So an expectation out of the in expectation we'd see the ratio of 0.5 plus 1 plus 0.8 times is to 0.5 plus 0 to 0.2. This is the ratio on expectation between bias and fair, right? We don't have exact counts, but we have an expectations. And now, does it not look very similar to the kinds of calculations we were doing here? So this is when the data was fully known. So there we were computing the number of times zj occurs at time t equal to 1. And there the count for bias was 2 and the count for fair was 1. Now we're saying that the expected count of n1b for our example is 0.5 plus 1 plus 0.8. So which is 1.5 plus 0.8, 2.3, and this is 0.7. Of course, these quantities should sum up to 3, given that you have 3 observations, right? So you do the remaining calculations as you were doing earlier in the case when the data was fully observed. So that's the whole crux of expectation maximization. You learn the different states or the expectations over the different states over different times in the different sequences, right? I just gave an example of how we can recompute the estimates of pi hat, right? You started off with some pi hat, you saw some observation sequence, and you also started off with some assumption on a hat and b hat and phi hat, and based on that we can calculate the expected number of times z1 for different sequences would be in b or f state, right, which is given by gamma 1b and gamma 1f. So now, as we've done for the fully observed case, as I just given a very simple example, we can use the same Emily principles to estimate pi 2, a2, phi 2, which are the estimates of pi a and phi at the iteration number 2. Right, so it's an iterative algorithm. But what we can do is to, instead of going the whole route and trying to see the values of each z at each time instance for each sequence, what is the expected state, we could just make our lives easier. We just compute the the expected sufficient statistics, which is the expected value of the sufficient statistics, where the two sufficient statistics are gamma I comma th for the jth state. So this is basically telling that for the ith sequence at time t evaluated for j. And if we look at the definition of epsilon t j again, so that's just the probability of being in state j at time t. as per the definition that since we're using j here. So that's just the probability of being in state j at time t for the ith sequence, which means that we have also observed xi 1 through t, right? For the ith sequence, we've observed the from 1 to t and given the model parameter theta. So to be very precise, you might also want to use t underscore I here, assuming that the sequences are of different lengths. And similarly, we also compute epsilon 1 t, where the arguments are j and k, the different states, which is given by z of t minus 1 is j and z of t equal to k, and conditional on the observations, full set of observations for that sequence, and the model parameter. So this is the E step, where we computing the expectation over the sufficient statistics. The M step is now we're going to be making use of these this expected sufficient statistics, and we'll be recomputing the variables or the parameters of concern. Right? So without much thought, you might also conclude that pi hat of k is just the expected frequency of zit being state k, right? So, which is the same formulation that fairly similar formulation that we'd seen in the case for fully observed data, but here we're talking in terms of expectations because we are talking about probability distributions and not the actual counts because the actual counts are unknown. So the expected frequency of zit equal to state k divided by, so which is just summation over different uh, sequences I varying from 1 through capital N of gamma I comma 1 and being in state k, so the argument is k, divided by the total number of sequences capital N. Right. So could you stop or could you pause the video for a second and think about what would be a hat jk? So that would be fairly similar. Now in terms of talking about just making use of expected sufficient statistics. So you could talk about a hat jk as the expected number of transitions from zt equal to j to zt plus 1 equal to k. Right. So the transitions you're making from j to k divided by the expected number of transitions from zt equal to j. Right. Where in the denominator you can, instead of going to just the kth state, you can go to any 1 through capital K states, right? So the numerator is just epsilon it jk. So epsilon it jk is the probability of being in state j and state k at time t and t plus 1 and observing the entire sequence. And this we're talking for the ith sequence, and we are summing it up for all the sequences from I equal to 1 to n and over all the timestamps. So this is telling you the expected number of transitions from j to k across all the chains and across all the timestamps in each chain. The denominator is just the normalization constant here, which is instead of looking at the transitions from j to k, you look at transitions from j to all I, where I varies from 1 through capital K. So there's just another term which is being added. Okay, so there seems to be a small mistake here. This should be a summation from k equal to 1 through capital K and not j equal to 1 to capital K. And in similar fashion, we can compute phi hat of JL. So phi hat of JL is going to be the expected number of times you are in state J and you're observing the symbol L divided by the expected number of times you are in state J. Right. So this can be written in terms of gamma. So gamma it of J, you're summing it over all the timestamps where xit is L. Right. And you're summing it up over all the possible, or given all the sequences, I equal to 1 through capital N. And the denominator is just the number of times you're in state J, which is just the summation over gamma it j from all the timestamps in a given sequence, t equal to 1 through ti, and summed over I equal to 1 through capital M. So the final piece which is left is, how do you initialize the thetas? How do you initialize pi a and b? So any thoughts on that? There could be multiple ways. The simplest way is to just randomly initialize with multiple restarts. So this is to say that you you choose a random set of values for pi a and b, which should of course adhere to all the constraints of the probabilities all summing up to 1. And after choosing all of these, after choosing a random initialization, you evaluate the score, or what is the log likelihood of the data given the final set of parameters which you update after convergence. And you repeatedly do this exercise, and you then finally end up choosing the parameters which gave you the best log likelihood of the data. So this is just randomly initializing with multiple restarts and choosing the best log likelihood set of parameters. Or you could initialize using some training data. So by training data, I mean that, let's say for a very small amount of data set, you know the fully labeled data. You know the values of the hidden nodes, the hidden variable zi, right? So if you know that, you could very well use that as a starting seed, and you could use those as a starting point and learn pi a and b, which could be then used to train on the much larger data set, which does not contain the hidden variable z's. Thirdly, you could also initialize using the Viterbi domain. Now, there is no single way to say which of them was the best way to do, and in practice, you might see multiple different ways in which the initialization is done. It's not uncommon to see random initialize with multiple restarts. So with this, we'll end the series on HMMs. We might additionally do some notebooks showing some practical use cases, but that's unsure for now. So with this, we'll end the discussion on HMMs.